All right. So we said that we are going to learn how we differentiate a function where you have more than just x raised to a power. And this is what the chain rule is used for. So after this, we have one more rule to learn about. It's called implicit differentiation. And that is where you need to differentiate a term that contains a y variable. We're going to see that we're going to have some expressions where not only are there x variables in terms, but also y variables in terms. So we're going to learn about differentiating those types of expressions using implicit differentiation, but it's also based on this chain rule. So we'll do that today. So the power rule says that if f at x equals x to the n, then f prime x, remember that's one notation for derivative, can be found by taking the exponent, bringing it in front as a coefficient, and then the power decreases by 1. But it cannot be applied when some base other than x is being raised to a power. For example, suppose f at x equals x squared plus 1 all cubed. If you use the power rule there by bringing the 3 in front, reducing the exponent by 1, you'd get 3 bracket x squared plus 1 all squared. And then if you multiply that out, that gives you 3x to the fourth plus 6x squared plus 3. However, if you took that original expression, the x squared plus 1, and expanded it out by cubing it, you would get x to the 6th plus 3x to the fourth plus 3x squared plus 1. And then the derivative of that would be different than what we got above. So this just shows us that you cannot use the power rule when you have something more than just x raised to an exponent. So this is where we use the chain rule. And it says, if f at x equals x minus a to the n, then f prime x, and so you'll notice that it does utilize the product rule for its first part, but then the second part is taking the derivative of what's inside the bracket. What's inside the bracket there is x minus a. That's the base that's raised to the power n. So you do use the chain rule or the power rule initially, but that's only part of it. That's the first factor. Because after you do that, you're also going to multiply by the derivative of what's inside the bracket. So let's go back and look at that. Y equals x cubed plus 1 all squared. We know from above that it must equal this first expression, this fifth degree polynomial. That's what it needs to equal, because that's what we got when we expanded it out. We simplified it first and then differentiated. So we should get the same thing if we use the chain rule on this expression. So let's do that. So if y equals x cubed plus 1 all squared, then the derivative, which would be dy by dx, so using the chain rule, 2 comes in front. Is that the same one? No, that one was x squared plus 1 all cubed. So no, that's completely different. I thought it was the same one, but it's not. But anyway, let's do this using the chain rule. So you use the power rule initially, and then you have to multiply by the derivative of what's inside the bracket. I guess we'll write it as x cubed plus 1. So that gives us 2 bracket x cubed plus 1. And the derivative of x cubed plus 1 is 3x squared. And then I multiply the 2 and the 3x squared together to get 6x squared. Bracket x cubed plus 1. So you can leave it in factored form, which is this is. You could multiply it out as well, doesn't matter. But there's our derivative. So question 2. like we've done before, we would write this as a power as our initial step. Square root means, square root means power 1/2. So we'd write it as a power first, and then we would differentiate. And again, we'd have to use the chain rule here because it's more than just x that's raised to a power. And the chain rule has 2 steps to it. You use the power rule initially, but then you also multiply by the derivative of what's inside the bracket. So there's a couple things we can do to simplify this. One of them, move the 3x plus 4 down to the bottom with the 2, and that'll make the exponent sign positive 1/2 instead of negative 1/2. And then when you multiply by the derivative of what's inside the bracket, that would just be 3, or 3 over 1. And then when you multiply those, we'll get 3 all over 2 times 3x plus 4 to the power 1/2, which we could also write as the root of 3x plus 4. Okay, so there's the derivative. Question 3, again, I'd start by writing that as a power. So the denominator is the root of 2x minus 1, which would be 2x minus 1 to the 1/2. We would move that to the top, and it would become 2x minus 1 to the negative 1/2. This just makes it easier to differentiate. You could leave it as the denominator, but then you'd have to use the quotient rule to differentiate. Root of the top times the bottom minus root of the bottom times the top all over the bottom squared. It would work, but it's easier if you write it like this. Then you don't have to use the quotient rule anymore, so we can just use the chain rule. So dy by dx equals negative 1/2 bracket 2x minus 1 to the negative 3/2. And now instead of writing down times d by dx of 2x minus 1, let's just take the derivative of what's inside the bracket, which would just be 2. So that 2 we multiply by the negative 1 on top here. So you'll get negative 2 over, and the bottom also has a 2 times 2x minus 1 to the positive 3/2. And the 2's would cancel here, so we would get negative 1 over 2x minus 1 to the positive 3/2. And there's your derivative. Now again, you could have done this one using the quotient rule right from the start. And when you take the derivative of the top, that's just going to be 0 times the bottom, which would still be 0. So you'd only have the second part of that, which is derivative of the bottom times the top all over the bottom squared. So it worked, but using the chain rule is probably a little bit easier. Number 4, again, we start by writing that as a power. Square root means power 1/2. So now f prime x, the derivative, first part of the chain rule is using the power rule on that function. And then you're going to multiply by the derivative of what's inside, which in this case will be a binomial, 4x cubed plus 2. So the 4x cubed plus 2 would stay on top. It is multiplied by the numerator on the 1/2, which is just timesing it by 1. So the numerator is 4x cubed plus 2 all over 2. And we could write it as a root if we wanted to, because when the x to the 4th plus 2x to the power negative 1/2 moves to the bottom, the exponent sign changes to a positive 1/2, which is square root. And it's possible, like we've said before, that if you were checking an answer in the back, they may rationalize the denominator by multiplying top and bottom by the root of x to the fourth plus 2x. They might. So that would give us 4x cubed plus 2 times the root of x to the fourth plus 2x all over 2 times x to the fourth plus 2x. So that's what that would look like. And there's nothing we can do to simplify this. Remember, you have to be able to cancel entire factors, not parts of terms, but entire factors. Okay? Doesn't matter what the power is, the rule is the same. So the 200 comes in front. Power decreases by 1. And then we're going to multiply by the derivative of what's inside, which will be 3x squared plus 4x. And there's not much we could do to simplify this. You could maybe take out a common factor of x in that last factor, but it would just go on to the 200 then. So it doesn't really help us in any way. Question 6. You can go straight to the derivative using the chain rule. The power decreases by 1, so that'll be negative 1/3. And then we're multiplying by the derivative of what's inside, which is 4x cubed plus 3. And then we can simplify a little bit. By moving the factor with the power of negative 1/3 to the bottom, and it will become positive 1/3, which is cube root. And so again, you could multiply top and bottom by the cube root of x to the fourth plus 3x to get rid of the radical in the denominator. And again, if you're checking answers in the back, that might be something they do. Okay. But we could definitely divide. Sorry, that 2 on the bottom is wrong. That should be a 3. The denominator was 3 there. Okay. So looking at number 7, again, we would start by writing it as a power. And then differentiate from there. So there's the first step. Oh, forgot to reduce the power by 1. And then multiply by the derivative of what's inside the bracket, which would be 9x squared plus 18x, take away 4. And then number 8, already written as a power, so we can go straight to the derivative. And when you decrease that power by 1, you're decreasing it by 2 halves. So if negative 5 halves take away 2 halves is negative 7 halves. And then when you multiply by the derivative of what's inside, it would look like that. And you might simplify this. The negative 5 would stay on top. That last factor would stay on top. And you might change that last term of that factor to 3 halves root x. The 2 is on the bottom, along with 3x cubed minus x to the 3 halves plus 2, and that power becomes positive 7 halves. So there's the derivative. So now we're going to see somewhere we have to use a combination of rules. Right? This initial expression here is a product. So we're going to have to use the product rule to differentiate. And then whenever we're differentiating a factor that has anything other than just x raised to a power, we're also going to have to use a chain rule as part of that differentiation. So that's what we need to do. So f prime x says, because it's a product here, we're going to take the derivative of the first factor, which we're going to have to use the chain rule to do that. This is the derivative of that first factor. And the first part of the chain rule is using the power rule, but we have to remember then we're also multiplying by the derivative of what's inside the bracket. So remember the product rule says you take the derivative of the first term, which is what we have written there, and then you multiply by just the second term. Not the second term, but the second factor. So that's the first step of the product rule. Derivative of the first factor times the second factor. Plus, now we have to take the derivative of the second factor, which once again will involve the chain rule. Chain rule has 2 parts to it. You use the power rule first as the first part of the chain rule, but then you're also multiplying by the derivative of what's inside the bracket, which would be negative 3. But then we also have to multiply that by the first factor. So there's the initial step for this derivative. Derivative of the first factor, which is a power, so we have to use the chain rule for that, times the second factor, plus derivative of the second factor, which again we have to use a chain rule for, times the first factor. So now we're going to simplify. I've got a factor of 3 and a factor of 2x. I'm going to multiply those two together and get 6x. And I have x squared plus 1 all squared. And I have my 2 minus 3x all to the 4th. Then when I look at that second term, I have a factor of 4 and a factor of negative 3. So I'll put those together. 4 times 3 is negative 12. And we can simplify this. We can take out a common factor. There are 2 terms here. Each term is divisible by 6 because you've got the 6x coefficient and the 12, actually negative 12 coefficient. So each term is divisible by 6, But if you also look at the two terms, each term contains a factor of x squared plus 1. In the first term, it's x squared plus 1 all squared. In the second term, it's x squared plus 1 all cubed. So there is at least an x squared plus 1 all squared in each term. Remember, when you're taking out common factors involving powers, you're going to take out the one that has the exponent that's the smallest. Also, there is common factors of 2 minus 3x here. And if we look at the two terms, the smallest power on 2 minus 3x is the one in the second term, which is the power 3. There's your greatest common factor. To get what's left, we divide each term by that common factor. So when you divide the 6x by the 6, you're just left with x. The x squared plus 1's all squareds cancel. You divide them by itself, so really you're going to get a 1 there. So that 1 represents what you get when you divide the x squared plus 1 all squared by itself. But then you're also going to divide the 2 minus 3x to the fourth by 2 minus 3x all cubed. Subtract the exponents, it'll be 2 minus 3x to the 1. So that's what you get when you divide that first term by the common factor. Now we'll divide the second term by the common factor. When you divide negative 12 by 6, you're going to get negative 2. The 2 minus 3x all cubed cancel. Or when you divide them, you're going to get 1. And then you're going to divide the x squared plus 1 all cubed by the x squared plus 1 all squared. Again, you're dividing powers with the same base. You subtract the exponents and keep the base the same. You're going to get x squared plus 1 to the power 1, or just x squared plus 1. So our final step then will be simplifying what's inside those big brackets. So you're going to have 1 times x, which is x, times 2 minus 3x, that'll be 2x minus 3x squared, minus 2x squared minus 2, when you multiply out those last brackets. So that'll give us our last term of negative 5x squared plus 2x minus 2. So there's the final simplified answer. And you know, if you were asked, let's say, to find the equation of a tangent line for this function at a certain point x, we use a derivative to find the slope of the tangent. You wouldn't have to do anything past that first step to evaluate that, right? You could just let x equal whatever the x value is at the point of tangency in that very first step and figure out what the slope of the tangent is. But there are going to be cases where we're going to follow this all the way through like I did here to simplify it. Okay, so we will be doing some of that, especially when we get to questions involving the quotient rule, because it's going to allow us to simplify it even more. You're going to get factors that are common in all terms that are going to cancel, right? So we will use this to simplify, but like I said, if all you're looking for is the slope of the tangent, you could stop after that first step, sub whatever the x value is at the point of tangency to find the slope of the tangent. So for this one, we're going to have to use a combination of the chain rule and the quotient rule. Also in this case here, the function is s in terms of t. So if we're going to write an expression for the derivative, we would say ds by dt, the derivative of s with respect to t. So remember, to differentiate a power, we use the chain rule, which has two parts to it. The first part is the power rule. So the exponent comes in front. For this step, what's inside the bracket doesn't change, but the power decreases by 1. but that's only the first part of the power rule, the second, or the chain rule. The second part is taking the derivative of what's inside the bracket. So d by dt of 2t minus 1 over t plus 2. So you differentiate a power like this using the chain rule, which has 2 steps. The first step is using the power rule. That'll give you your first factor, but then that's multiplied by the derivative of what's inside the bracket. And that's what d by dt means. It means the derivative of what's inside the bracket. And to differentiate what's inside the bracket, we have to now use the quotient rule to do that. So this first factor isn't going to change. And now that's multiplied by, again, to differentiate what was inside the bracket, we have to use the quotient rule, which is derivative of the top times the bottom minus the derivative of the bottom times the top all over the bottom squared. Again, we talked about, as we go through this course, there's going to be some parts of it that are going to be heavy in the algebra. So let's simplify. So you're going to have 2t plus 4 minus 2t plus 1 all over t plus 2 all squared. So we can certainly simplify the numerator of that second factor. And the other thing I'm going to do here, let me just back up a little bit. The other thing I'm going to do here is that second factor, that power of 2t minus 1 over t plus 2 to the fifth, I'm going to break it up. And you'll see why I'm doing this in a minute here. So that they're both to the power 5. So the top, the 2t's are going to cancel. You're left with 4 plus 1, which is 5. And the denominator is t plus 2 all squared. So you see the reason why I broke up that second factor is now I can multiply top times top times top over bottom times bottom. And that'll give us 6 times 5, which is 30, bracket, 2t minus 1 to the fifth. And on the bottom, I'm multiplying two powers with the same base of t plus 2, so I can add the exponents. And I will get t plus 2 to the power 7. There's our final simplified answer. So, I mean, as you're going through this, you hopefully would recognize that those denominators have the same base of t plus 2. So they can be combined. Add the exponents, keep the base the same. That is the reason why we split up that second factor, so we had both numerator and denominator raised to the power 5. This makes it easier to see that last step. All right, question 11. We've got a radical within a radical. Like we've done before, we would start by writing these as powers. So it'll be x plus the x squared plus 1 is raised to the power of half, and the whole thing is raised to the power of half, because it's all under that first radical. So sometimes you're going to use the chain rule within the chain rule. And this is one of those steps. So let's see how this works. dy by dx will equal. So to differentiate this, we have to use the chain rule. The first step is using the power rule. So this power of 1/2 on the outside is going to come in front. So it'll be x squared plus 1 to the, sorry, not x squared. I'm not sure why you squared that x. It's x squared plus 1 all to the power 1/2. And then this power decreases by 1 to negative 1/2. But then we have to take the derivative. We multiply by the derivative of what's inside that big bracket. And what's inside that big bracket is x squared plus 1 to the 1/2. That's the chain rule. Use the power rule as your first step, but then you're multiplying by the derivative of what's inside the bracket. And now when we differentiate what's inside those big square brackets, we're going to have to use the chain rule again when we differentiate that second term, because it's also a power, x squared plus 1 to the 1/2. So I've got the 1/2, I've got x plus, I did it again. I'm not sure why I keep wanting to write x squared there, but fix that. So it's x plus x squared plus 1 to the power 1/2. That's all raised to the negative 1/2. So that's just that first factor written out again. And now we're going to multiply that by the derivative of what's inside the square brackets. So we're going to differentiate that. The first term will just be the derivative of x, which is 1, plus, when we differentiate that second term, we have to use the chain rule again. Whoops. Chain rule has two parts to it. The second part is multiplying by the derivative of what's inside the bracket, which would just be 2x. So we can start to simplify this. This first factor has a numerator of 1. Because this is all raised to the power negative 1/2, we can move it down with the 2. And we can write it as radicals if we want. So it'll be the root of x plus the root of x squared plus 1. And that's going to be multiplied by 1 plus. So what's going to happen here is when you multiply the 1/2 by the 2x, 2's are essentially going to cancel. And so we're just going to have 1 times x on top over the root of x squared plus 1. And that's how I'm going to leave that. Again, if you wanted to know the slope of the tangent, you would want all those powers to be positive. So you'd want to do this step in order to find the slope of the tangent. Okay? So here's something a little bit different. You want to find the derivative of y with respect to t at the point when t equals 2. However, if you look at what you're given here, you're given two different expressions. The first one is y in terms of a, the second is a in terms of t. So there's a couple different ways you can do this. Okay, there's a couple different ways you can do this. One of them would be to substitute what you have for a equals t plus 1 over 3t minus 2. You can substitute that back into this first equation and simplify, and then differentiate, because that will give you an expression for y in terms of t, because that's what we want to find. We want to find dy by dt, the derivative of y with respect to t. So if you're going to do it by the way we have been differentiating, you'd have to first have an equation or an expression where y is written in terms of t. So you could do that by substituting whatever a equals, t plus 1 all over 3t minus 2, by substituting that in for the a in the first expression, and then simplifying and then differentiating. But there's another way that we can do this, and it starts by writing an expression, an equation that we haven't seen yet, and that is this. You can write dy by dt as an equation. You can say that equals dy by dA times dA by dt. So where do those come from? Well, the first expression is y equals the root of 1 plus a. It is y in terms of a. If you want to find the derivative of this first expression, it would be dy by dA, the derivative of y with respect to a, right? And the second expression we have here is you're multiplying by dA by dt. Well, that would be the derivative of the second expression. The second expression is a in terms of t. So the derivative of that would be the derivative of a with respect to t, dA by dt. And if you look at this expression that we've written here, you could cancel the dA's and you'd be left with dy by dt, which is what the left side is. So that shows that this is an equivalent expression. If you cancel the dA's on the right there, you're left with dy by dt. Okay? So let's work with this. Before we differentiate this first expression, we would want to write y as a power. And now we will differentiate that. So dy by dA would be 1/2 1 plus a to the negative 1/2 times the derivative of what's inside. The derivative of a, first the derivative of 1 is 0. The derivative of a is just 1. So there's dy by dA times dA by dt, which we would have to differentiate this one using the quotient rule. Derivative of the top times the bottom minus the derivative of the bottom times the top, all over the bottom squared. So this is going to give us 1 over 2 times the root of 1 plus a as our first factor, simplified. The second factor we will also simplify. Don't make the mistake of canceling a 3t minus 2 on top and bottom, though, because the second term on top doesn't have a 3t minus 2 in it. And we have to be able to cancel the same factor in all terms, not just two of them. We've got three terms here. Only two of them have a factor of 3t minus 2. So that means we're going to have to multiply this out. We'll get 3t, take away 2, minus 3t, take away 3, all over 3t minus 2 all squared. So we can simplify this out even more just by working on that second factor. So the 3t's are going to cancel. You'll have negative 2 take away 3, which is negative 5, left as the numerator, all over 3t minus 2 all squared. So we want to find the value of this when t equals 2. And we have the variable t in here, right there. So we can let t equal 2 there, but the other issue is we also have a variable a here. But we can find out what a equals when t equals 2 by going back to the original expression where a is written in terms of t, and we can find out what a equals when t equals 2. So the top will be 2 plus 1, which is 3. On the bottom, you're going to have 3 times 2, which is 6. Take away 2, which is 4. So when t equals 2, a equals a half. Did I do that right? I'm sorry. This should be 3/4, not 1 2/4. Apologize. Because it's 2 plus 1, which is 3. So 3/4 is the value of a when t equals 2. So now we can plug those values in here to get the value of the derivative dy by dt at the moment when t equals 2. So we're going to have 2 on the bottom times the root of 1 plus a, which we found to be 3/4. And that's multiplied by negative 5 over, and when t equals 2, 3 times 2 is 6, take away 2 is 4, squared is 16. So I can multiply top times top and get negative 5 on top. On the bottom, I got 2 times 16, which is 32, times the root of 7/4, because you're going to add 1, which is 4/4 to 3/4. So I can do a bit more simplifying here. On the bottom, I can break the root 7, make it root 7 over root 4, because the square root of 4 is 2, so it'll be root 7 over 2. And then 32 divided by 2 is 16. So that'll give us negative 5 over 16 root 7. And if I rationalize that, it'll be negative 5 root 7 over. On the bottom, when you multiply that by root 7 times root 7 is 7. And 7 times 49, or times 16, I apologize, is 112. So there's your answer. There's the value of dy by dt at the moment when t equals 2. Okay? So we'll be going through the LIMS exam this week. So we'll be doing that. We're also going to be having a quiz on derivatives. I'll figure out for sure what day we're going to do that. We're not going to have an exam after this chapter, after derivatives, because we're going to go into applications of derivatives next. And then after that chapter, we'll have an exam, because we're going to be using everything we've learned in this chapter in the next chapter as well. So after the next chapter, we'll have an exam where there's questions about derivatives and then applications of. So we're going to see other ways that we use derivatives as well, besides just finding the slope of the tangent or the instantaneous rate of change. Okay, so you want to work on those questions. I'll post those solutions in Google Classroom so you can check your answers. Again, I strongly encourage you to do these questions. The practice is important when it comes time for writing that quiz and writing the test.